Hey guys, let's start with today's lecture. Today we are going to study about permutation matrix, orthogonal matrix, and PA equals to LU decomposition. About permutation matrix, orthogonal matrix, and the PA equals to LU decomposition. Now earlier we studied how to solve a system of linear equations, right? So to solve a system of linear equation, we convert our matrices into a upper triangular form, right? That's what we have studied so far. Now for a system like this, where we have where we have 0 in the pivot position and underneath is a non-zero entry, how can we convert the system into a upper triangular form? Now this is considered as a failure, but this is temporary because previously we studied that elimination, the process of elimination may fail in the two ways: when our system has no solution or our system has infinitely many solutions. Now both of these are considered as permanent failures because for no solution, no matter what value of y you put, this system can never be satisfied, this equation can never be satisfied, right? So this is considered as a permanent failure. And for the second system, we have only one pivot because we have no pivot here, pivot can only be non-zero, and our number of linear equations is 2. So for our system, the number of pivots is less than the number of linear equations, hence this leads to infinitely many solutions, and this is considered as the permanent failure as well. Now the third one that we are now going to encounter is also a failure, but rather temporary, which means that it could further be resolved. Now if I take my previous example, where we were given a system where we have 0 in the pivot position, how we can resolve this is by swapping two rows, and this is known as row exchange operation. So if I swap my row 2 with row 3, the resultant matrix that I'm gonna get is now in the upper triangular form. So this failure is resolved through the operation that is known as row exchange operation. So our row exchange is needed when 0 is in the pivot position. Now to perform this row exchange operation, the matrix multiplication that we use is known as the permutation matrix, right? So for the elementary row operations, we had elementary matrices, and for the row exchange operations, we have permutation matrix. Now how do we produce a permutation matrix is similar to the elementary matrix, where we take our identity matrix I and uh, we perform we apply the same row operation that was intended for a matrix A to the identity matrix I, and the resultant that we are going to get is known as the permutation matrix. So I'm going to apply the same operation on my identity matrix. Previously it was R2 swapped with R3, and the resultant that I'm gonna get is the permutation matrix, which is denoted by P23, which basically denotes that my R2 is swapped with R3. So the definition is a permutation matrix P has the rows of the identity I in any order. Now our rows can be arranged in any order. This is just one way. So our permutation matrix has the rows of the identity in any order as long as it is distinct. It is known as the permutation matrix. One key point to remember is that for any row, we should only have a single one, and the rest of the entries should be 0. Then only it is considered as a permutation matrix. Okay. Now to find out the number of permutation matrix of order n, we have a formula n factorial. Now why do we have so many permutation matrix? Now in this case, what you are going to observe is that our identity matrix is also a permutation matrix because it fits the definition that we require a single one and the rest of the entries are 0. So this is a permutation matrix. Now we did a single row operation and we acquired this matrix, right? So this is one way to produce a single row operation permutation matrix, but we can swap any two rows, right? Or we can do them multiple times as well. So that's why we have multiple number of multiple number of permutation matrix, and it is of order n factorial, right? That is one way to find out the number of permutation matrix, and it is the number of ways in which the rows can be arranged so that it produces distinct permutation matrix every time. Now for n factorial, all of the n factorial number of matrices are going to be distinct. So apart from n factorial, any matrix that we are going to obtain is going to be same as the as any matrix in the n factorial, right? So this n factorial are the distinct permutation matrix. Okay. Now let's take one example where I have taken the order 3. Now for order 3, how many number of distinct permutation matrix that I am going to obtain is n factorial, that is 6. Okay, so I have 6 permutation matrix of my of order 3. Now my I, that is the identity matrix, is the standard permutation matrix. Now out of these six matrices, 4 of these are single row operation. That means that we have acquired them through single row operation only. We have only operated single row operation on them, and we have acquired our permutation matrix, and the rest two are known as the multiple row operation. That means we have operated row exchange operations multiple times to acquire our permutation matrix, and hence these are known as the multiple row exchange operation matrices. Okay, now out of these 6 matrices, 4 are their own inverses. Now you will observe here that the matrices that we have obtained through single row operation, they are their own inverses. That means if I multiply this matrix with itself, we are going to obtain identity matrix. Now why so? Because let's assume here I have swapped row 2 with row 1, right? So if I do this, if I perform the same operation again, like if I have swapped R2 with R3, and if I perform that same operation again, I'm basically undoing my operation, right? So that is why if I multiply this matrices with itself, we are going to obtain identity matrix, because we are basically undoing our operation. So out of these 6, 4 are their own inverses. What are those 4? That are single row operation. Okay, but for multiple row exchange operation, the inverse is in the reverse order. Basically the inverse of the multiple row exchange matrix, the inverse is of the reverse order. Now one way to understand this is through the example of wearing a shoe. Now how do we wear a shoe? First we put the socks on, and then we wear the shoe. So this is putting the socks on and then putting the shoes on. Now how do we take them off? First we remove the shoes, and then we remove the socks, right? So that is how we undo an operation. That is how we remove a shoe or undo an operation. And in the similar fashion, we calculate the inverse as well. That means the inverse is of the reverse order. Okay, now one important note is that P inverse is also a permutation matrix. Why so? Because permutation matrices form a group of multiple matrix multiplication. Now since there are only n factorial distinct permutation matrix of order n, the inverse of the permutation matrix will also lie in that group only. That means our P inverse would lie in the n factorial group only, because it will always preserve the property that one of the entry in the row is 1 and the rest of them are 0. That property is always preserved in the P inverse. So the result P inverse is going to be in the n factorial only. So this is also a permutation matrix. Now to study the next property of permutation matrix, we first need to study about orthonormal vectors and orthogonal matrices. Now this is going to be just the intro. We are going to study a bit more in detail in the upcoming lectures. Okay. Now what are orthonormal vectors? Orthonormal vectors consist of vectors that are orthogonal. That means they are always perpendicular and they form the basis of a matrix, and each of these vectors are of unit length. Now one prime and standard example is our identity matrix of a basis vectors that are perpendicular to each other and are of unit length. Now what is identity matrix? We have I cap and we have j cap. They both are perpendicular to each other and they are of the unit length 1. So our identity matrix is our vectors in the identity matrix are the orthonormal vectors. Okay. Now orthogonal matrix. Now A is orthogonal if its row and columns are orthonormal vectors. So when we take a matrix where the vectors or the columns consist of orthonormal vectors, then it is known as orthogonal matrix. But geometrically the definition of orthogonal matrices is that that it preserves the length and the angle of a vector. It doesn't stretch or distort the vector. It basically simply rotates the vector in the space. What does orthonormal matrices do is that it takes the vector and it basically rotates it into the space. It doesn't change its length. Its angle is preserved. Angle between the two vectors is also preserved. I'm going to explain that. And it doesn't stretch or distort like a scale. Earlier we used to scale our matrices. It doesn't distort it in that way. So orthogonal matrix basically transforms the vector from one position to another position. It basically rotates it and it doesn't do anything apart from that. Okay. Now this leads to the key properties that the length is always same. So before and after the transformation, length of the vectors is going to be the same, and the angle between the two vectors in the space before and after the operation is also going to be the same, right? So now this is our orthogonal vector. Now this is the general form of the orthogonal vector of order 2, right? So if I put any value of x, value of x is how much we wanna rotate it, right? So if I want to rotate it by 30 degree, so I would just put the value of in radians and then calculate it, and the resultant I'm going to get is the orthogonal vector. Now if I take its transpose, let's assume, right, and if I multiply them together, I do the matrix multiplication, the resultant I'm going to get is the identity matrix, and that is the key property. One of the most important property of the orthogonal matrix is that its multiplication with its transpose gives us the identity matrix. Now what are we computing here? Now if you observe carefully, what basically this is the dot product of the columns of A, right? So why is it giving us I is because of the properties we studied earlier, or the characteristics. So when I is equals to j, that means for the on diagonal for the diagonal entries, the dot products leads to 1 because because its length is always 1, right? The length of the entries vectors is always 1. So for the on diagonal elements, the dot product comes out to be 1, but for the off diagonal entries, the product of them is 0 because the vectors are perpendicular to each other. Hence the resultant that we get is the identity matrix. Now one important note or point that we can infer here also is that the transpose is equal to the inverse of the matrix. That means the transpose is same as the inverse. Okay, so all permutation matrices are the orthogonal matrix. Okay, now let's head over to Marino to fully grasp what do we mean by orthogonal matrix. Now let's take the example. Now let's see this more intuitively, how we can rotate our vector. Now let's assume I can take my matrix size to any of the order. Let's assume I take the order 3, right? Now this is my vectors. Now if I rotate them by 45 degree, all of my vectors are now rotated by 45 degrees. So the vector basically it adjusts itself without changing its length. That means our length is preserved, but they are basically rotated in the space, right? So you can do this for the order 2 as well, and you can change its angle to any value and see for yourself, right? So do play around yourself to make the concept more intuitive, right? Do come here and play around yourself. Okay. Now the last topic for today is the PA equals to LU decomposition. We so far studied different types of decomposition, which could be further factorized into triple product as well, known as the LTU decomposition, right? Now but when we encounter a system like this, where there is a zero entry in the pivot position, we first need to fix the system by first swapping the rows, which is known as the PA. The resultant is known as the P dot A, and then it is converted into the upper triangular form. So first we swap the values so that there is no 0 in the pivot position, and then we operate it in the similar fashion in the similar fashion like we did before, where we operate it through elementary operations and we obtain our upper triangular form, right? Okay, so and then it is further decomposed into LU decomposition. So this type of decomposition where it is first converted into an upper triangular form. First we swap the rows. So this is known as the PA equals to LU decomposition. So if a is invertible, the permutation matrix will put rows in the right order to factorize it into P dot A is equals to LU decomposition. So in this lecture we studied about permutation matrix, orthogonal vectors in matrices, and PA equals to LU decomposition. And that's it for today. Thank you.